Maxwell's equation. Del operator del dot E, divergence of E is equal to rho divided by epsilon zero. Del is del operator E, electric field intensity, sigma, current density, epsilon zero, permittivity. Permittivity of free space. Now, what is electric field? What is the vector field? Vector field can be shown like this. If we have positive charge, then another positive charge kept here will repel in this direction. Charge kept here, positive charge, that will also repel very strongly. Charge kept at this point, it will also repel, but not strongly, weakly, because it is larger distance. Charge at this. So everywhere you will find the electric field. As you go away, the intensity will decrease. Now this is the electric field. It is a vector field. So the electric field is spreading out, and what the divergence of electric field gives you, it gives you the electric flux density. Divergence shows that the field is spreading, or whether it is spreading in or spreading out. Now in this case, suppose we have negative charge and here we have positive charge, it will attract it like this. So here also it will attract it, but weakly. Here also we have strong attraction for the positive charge. Here we have weak attraction. So what you can see, as you go away, the vector it becomes smaller, and when you, so here the field is spreading in, and divergence shows that divergence of vector field will give you whether the field is spreading in or spreading out. So this is the vector field of positive charge, this is the vector field of negative charge, and divergence of E gives you the charge per unit volume, that is rho. It gives you the charge density. And what is the permittivity? It is the constant, and definitely it will affect because it shows the permittivity of the medium, how much the ability of that medium to permit the electric flux. Second is divergence of B. So here we have the del operator, and here it is the magnetic flux density. So let us see magnet and see whether the magnetic field is spreading out or spreading in, and you can see the magnetic field neither spread nor spreading. So neither spread out nor spreading. Just for the coil also, we pass the electric current to the coil, we have the magnetic lines like this. These are the parallel lines, but see, on a larger account you can see these lines will the circular one, and there is no spread in or no spread out, and that's why the divergence of B is 0. This is the Maxwell's second equation, right? Now third is curl. So when you take the cross product of del operator with electric field, then you will get the changing magnetic field with respect to time. It means that whenever there is a rate of change of magnetic field, it will produce electric field. Again, for the physical significance of curl, curl shows the rotation. There is a rotation or not. So when we have the changing magnetic field, then you will get the electric field like this. That means if we have a certain coil, and if we have the magnetic field which is pointing inward, and if this magnetic field changes with the time, inside, outside, inside, outside, then the electric current will flow, the charge will flow in this conductor, right? So there is a rotation, and curl gives you the rotation. Now fourth Maxwell equation, curl of B. So curl of B gives you permeability into the current density. That means if we have conductor and current flowing through this produces the rotating magnetic field. Now in this case, as the direction of current is upward, the lines will be like this, magnetic lines. So rotation, so curl always signifies whether there is a rotation or not. So if the current is flowing downward, the magnetic field will be like this, right? And again it is found that rate of change of electric field also produce the rotating magnetic field. So daily by del T, permeability, this is permittivity. This can also produce the changing magnetic field. So flow of current produce the rotating magnetic field, and even the rate of change of electric field can also produce the rotating magnetic field. So these are the four equations. In first two equations, what we shall see the divergence of electric field and magnetic field, and divergence shows you whether the vector field spread out or spread in, right? If it is positive, then it is spread out. If the divergence of this vector field is found negative, then it is spreading in. Now for the positive and negative charge, we can have this electric field, and if take the divergence of this electric field, then you will see there is a flux density, that is the charge per unit volume. Then divergence of magnetic field is equal to 0. Divergence of magnetic field, here we have not spreading lines inside or outside, but the lines are like this, magnetic lines. So divergence of magnetic flux density is found to be 0. So the first two Maxwell equation shows the divergence of electric field and divergence of magnetic field, and the second two equations, Maxwell's equations, gives you curl of electric field intensity and curl of magnetic field induction. So del cross E, that is curl of intensity, electric field intensity, is the del B by del T. Rate of change of magnetic field is to time produces the electric field intensity. That is the Faraday's laws of electromagnetic induction, right? And here in this case, the current will produce the rotating magnetic field. The changing electric field will also produce the this magnetic field. So curl of B gives you mu 0 J. It is mu 0 is the permeability. Mu 0 and epsilon 0, permeability and permittivity. So divergence del of dot E is equal to flux density upon epsilon 0, and it shows the whether the flux is spreading out or spreading in, right? And del dot B also shows that it signifies that the single north pole or single south pole is not there. The lines, magnetic lines will not like this, and magnetic lines will not like this, like a positive or negative. They are always in dipole form, and the lines not spread, but they are like curved one. So these are the four Maxwell's equation, very simple to remember. First, we have divergence of electric field intensity and divergence of magnetic field flux density. Then curl of electric field intensity and curl of magnetic field induction. So curl of divergence of electric field intensity gives you the flux density, that is the charge per unit volume at that particular point, and the divergence of magnetic field will be 0. Curl of E, electric field intensity, gives rate of change of magnetic field with respect to time, and curl of magnetic induction gives you mu 0 into current density, that is current can produce the rotating magnetic field, and mu 0 epsilon 0 daily by del T, means changing electric field can also produce the magnetic field. Thank you.